Greetings, everyone. This is the free response question number 2 from the AP Calculus BC exam in 2018. Let's take a look at it. Ideally, you pause the video right now and go try to solve this on your own. That way, when I start talking about it, you have a sense of what it takes to solve it, and you know what you were thinking, and you can compare that to what I was thinking. And you'll be better for it. This says researchers on a boat are investigating plankton cells in a sea. At a depth of h meters, the density of plankton cells in millions of cells per cubic meter is modeled by this P of h, maybe that's a rho, my eyesight, I think it's P, is equal to 0.2 h squared times e to this negative 0.0025 h squared, where h is between 0 and 30 inclusive, and is modeled by a function f of h for h greater than or equal to 30. The continuous function f is not explicitly given. So we know the function for the depth less than 30 feet, less than or equal to 30 feet, but greater than or equal to 30 feet we don't know. They start with a pretty straightforward question. We want to find p prime of 25, and then we have to use correct units to interpret what p prime of 25 is in the context of the problem. Now I'm going to pause the video so I can write some of this down, and then I'll talk about it. I'm not going to do all the work off camera or while it's paused, but just to save some time, I'm going to pause it. So we want to find p prime of 25, where p of h is this expression here. Now, since this is the calculator section, I don't want you to go ahead and start trying to take the derivative by hand for this thing. It's well within our abilities, but we don't want to do that because we have a calculator available to us, and a skill that we are allowed to use on the calculator is to use the calculator to find the derivative at a point. So on your calculator, you're going to, however, whichever calculator you're using, use your calculator feature of taking the derivative at a point, type this function in, make sure you evaluate it at 25, and if you do so, you get about negative 1.179. Now this is in millions. If we remember back to the original description of this, it said at a depth of h meters, the density of plankton cells in millions of cells per cubic meter. So it's not just negative 1.179, it's negative 1.179, and there are other millions and other units that go with this. So, all right, so we have to interpret this, and we have to use correct units, interpret what this means. So we have to mention, when we're interpreting this, we want to mention every little piece of this. So I want to mention the 25 and its units, which are in meters, and I want to mention this, which now has units of, well, it was given in millions of cells per cubic meter. Now we took the derivative of that, so it's going to have another per cubic meter there. No, I'm not another per cubic meter, another per meter, because we're differentiating with respect to the altitude or the depth, which is given in meters. So we're going to have to take the units that we were given and divide that by meters. So this represents, at a depth of 25 meters, the density of plankton cells is changing. You can say decreasing, you can say changing at a rate of negative 1.179, or you can say decreasing at a rate of 1.179. If I use the word decreasing, I'm not going to use the negative. Million cells per cubic meter per meter, or technically, million cells per quartic meter, meter to the 4th power. But you don't have to write it like that. I'm not going to write that down. I'll repeat it one more time, but you want to say something like this. At a depth of 25 meters, so I'm referencing the input, the density of plankton cells is changing at a rate of negative 1.79 million cells per cubic meter per meter, or something equivalent to that. Let's go to part B. Part B says, consider a vertical column of water in this sea with horizontal cross-sections of constant area, 3 square meters. To the nearest million, how many plankton cells are in the column of water between h equals 0 and h equals 30? I thought this question was challenging because you really have to pay attention to the units. You have to know a little bit about density because that's what's referenced over here. And if you look at the units on this, it's millions of cells per cubic meter, and I'm trying to get a total. I know the cross-sectional area is 3 square meters. So when we have our millions of cells, I'm just going to put cells. Whoops, if it's hard to read that. Cells per cubic meter. When I multiply that by meters squared, I'm going to get millions of cells per meter, which is what I'm going to want to integrate in order to get the total number of cells. And so when I set this up for part B, I'm going to have to integrate from 0 to 30, because that's the depth at which we're using this density function, and it's got to be 3 times that density function with respect to h. And like I said, the reason why we're multiplying by 3 is 3 represents the cross-sectional area. The density is per cubic meter, so it's really this number of cells in a volume of water. So we're going to want to multiply that by square meters to get it as a rate per meter. And then when we're integrating that per meter, we're going to end up with just the total number. Luckily, this is something you could just run through the calculator, and you get about 1,675.4149, etc. Remember, we want at least 3 decimal places, so you can truncate around at that point. And also remember that this represents the number of million plankton cells. Okay, so it's not that there are 1,675 approximately plankton cells. There's 1,675 million plankton cells approximately. Now the question said to the nearest meter, so you'd actually round this to 1,675 million plankton cells in this column of water. All right, let's go back and figure out what C is asking of us, and I'll get rid of some of this mess here. All right, C is saying there is a function u such that f of h is trapped between 0 and u, possibly inclusive, for all h greater than or equal to 30. And we know that this improper integral from 30 to infinity of u of h dh is equal to 105. The column of water in part B is k meters deep. K is greater than 30. So that means we need to use this function f and the original function. Write an expression involving one or more integrals that gives the number of plankton cells in millions in the entire column, and explain why the number of plankton cells in the column is less than or equal to 2,000 million, which is not a normal way of writing numbers, but it is a legitimate way, certainly, to write this. So we have to break this down into its sections here. So in part C, we have the depth of water, so we have 30 meters down, from 0 to 30, and then we have to K after that. Okay, so we have to break it down into those sections. All right, I'm back. I had to pause because somebody had come by. So we want to figure out, we're looking for, I should have read this over again. So we're trying to figure out the number of plankton cells, and then we have a depth K greater than 30. So we're going to have to break this up because it's piecewise defined into 2 separate integrals. Now we actually already calculated the first one. So the first one is going to be the integral from 0 to 30 of 3 times P of H. This was our answer from part B. And then after that, remember, we have a different function from 30 onwards. So from 30 to K, we're using the function f. But we're still going to multiply 3 times that function like this. Okay. So I'm going back. It says write an expression involving one or more integrals. We've got our 2 integrals. That gives the number of plankton cells in millions in the entire column. So this would be the first part of the question. So now what we want to do is we want to know. So we already know the value of the first one. Here is whatever we said before, 1,675 million. So we were also told in the problem that f of h was less than or equal to u, and that u was bounded by this. Okay, so then I know that's 105. So just so I get this back, let's get a new screen here. Let's work on this second part here. So the integral from 30 to k of 3 times f of h dh, this is going to be less than or equal to the integral from 30 to k. I'm sorry, I'm having a little technical difficulties here for a moment. The integral from 30 to k of 3 times u of h dh, because we know f is less than u, less than or equal to u. So we know this is true, okay? I'm sorry, not from 30 to k. This should be from 30 to infinity. I forgot that that was an improper integral, so let me fix that. And then we know that this value here, or let's say that, let's do one more step of algebra. Let's factor out this 3, and then we get 3 times the integral from improper integral from 30 to infinity, u of h dh. And I know that the improper integral is bounded by 105, so that this is going to be less than or equal to 3 times 105, which of course is just 315. So I know the second integral in my expression from earlier, this one right here, is going to be less than or equal to 315. So if I go back over here, I know that this whole expression here, and I'm going to put a less than or equal to here. This is everything above is going to be less than or equal to the 1675, just substituting in the value that we found earlier here, plus the 305, which is equal to, what is that, 1980 million, and that is less than 2,000 million. So that's what they wanted you to do for all of this. So it is less than 2,000 million, like they wanted. All right, let's get on to part D. And then part D says the boat is moving on the surface of the sea. At time t greater than or equal to 0, the position of the boat is x of t comma y of t, where x prime is that expression and y prime is that expression. Time t is measured in hours, x and y t are measured in meters. Find the total distance traveled by the boat on the interval from 0 to 1, time interval from 0 to 1. So we should know that our total distance integral in parametric form is just going to be from integral from 0 to 1. We're going to have x prime of t squared plus y prime of t squared. Split the square roots. The dt is outside the square root. That's our total distance integral. So all you have to do is now plug in those expressions, plug them into your calculator. It comes out to about 757.45586. And that's it. You get 1 point for the integrand, 1 point for the total distance. So this was, in my opinion, one of the more challenging questions in recent years because of the notion of having to use density and multiply the density per cubic meter times the square meter in order to get a rate per meter, so that when you integrated per meter you would get a total number. So that was a bit challenging, but hopefully this year they won't ask something quite so intricate. Go study.